Right, let's finish this last question off. But before I do that, no, what I'll do is I'll summarize it at the end actually. Go on. Right. So a ray of light enters a glass block and is refracted. Right, now watch this. So I want you to know this, that air is optically less dense. This is optically more dense. Right, so you've got a ray coming in. That is the incident ray. This angle here is the angle of incidence. It's important, and I'm emphasizing it again, that put these words into your head. That there is the normal. It's at 90 degrees. Look, it's at 90 degrees to the boundary. And finally, this is the angle of refraction, and this is the refracted ray. Right, when you go from an optically less dense, I always get this wrong, so just try to remember it. When you go from an optically less dense medium to an optically more dense medium, the refracted ray moves towards the normal. Okay, so it moves towards the normal. Right. Bear with me 1 second. Okay, so that's why. So it moves from an optically less dense to an optically more dense. So it will move towards the normal. Right. Because the ray goes from an optically less dense to an optically more dense medium. Right. Opals and diamonds are transparent. They allow light through. Jewelers shape the stone so that light is reflected inside. Figure 2 shows the path of a ray of light that enters and leaves, and you have total internal reflection. Okay. State the equation linking the refractive index and the critical angle, refractive index. So N is what is it? Sine I over sine R. And I think there's another one. Right. What we want is this one here. Sine C equals 1 over N. N is the refractive index, so this is the one that they want. They don't want that one. I'm just going to go make a note of these two up there because they're useful to know. Yeah, so this is the one that they want because it's got the refractive index, which is this, and the critical angle, which is C. Right, we're here, so let's write this down. Number 9. was it sine C, the sine of the critical angle is 1 over n, and the critical refractive index is the sine of the angle of incidence over the sine of the angle of refraction. So these are two formulae that you'll be given them, but it's good to know. Right, let's go back. Right, the critical angle of opal is 43 degrees. Show that the refractive index of opal is about 1.5. What did they say? Show that, right, okay, so they've said the critical angle, they've given us that, they've given us this, and we just need to rearrange this formula. So let's do it in physics mode. So we're saying sine 43 is equal to 1 over n, so therefore n equals 1 over sine 43. So n equals 1.47, which is approximately 1.5, yeah. And you've just shown that. Yeah, we'll leave it like that. That's the 2 marker. The refractive index of diamond is 2.4. Explain why rays of light inside a diamond are more likely to be totally internally reflected than inside opal. Right, got no more questions, so right, when you have a larger refractive index, larger n, this means that the critical angle, because it's the equation, isn't it? It's sine C equals 1 over n. So when n is big, C has to be small. So the critical angle is smaller. So diamond has a larger range of angles for total internal reflection, TIR, total internal reflections. Could you do that? Then what they're saying is you can do an example. So we're saying sine C equals 1 over 2.4. So C equals 25. If you put that into your calculator, where is the calculator? Right. You know how to work out the angle. It's inverse sine. So you'll do shift sine 1 divided by 2.4, close the bracket, equals 24.6. So they've rounded off to 25 degrees. So right, so what's going to happen is, you try to understand this here. No, let's not draw it that way, it might confuse you. Right, let's try this again. Right, there's the boundary, there's the normal. So for diamond, that comes in, that has to be 25 degrees. Right, anything more than 25 degrees, you get total internal reflection. So what they're saying is you have got 65 degrees where it's going to be totally internally reflected. Now let's do the same thing with opal. There's that. There's the normal. What angle did they say? 40. Yeah, 43. There. Okay. So this is 43 degrees. This will be there for 40. What are we? That will be 40. Come on, 47 degrees. Right. Now, so that means here, if you look at this number, you've got more angle, a bigger range compared to. No, that's horrible. Should we try that? Yeah, okay, that's a bit better. Where the total internal reflections occur, so it's going to bounce around more internally and look better. Right, let's go back. Let's go back to the. Right, there you go. So we know refraction is the change in direction of waves at a boundary. You've got the incident ray, refracted ray, angle of incidence, angle of refraction. The refractive index is sine I over sine R. The higher the refractive index, the more the material bends light. You've got two types of wave: longitudinal, which are like sound waves. They vibrate along the direction of travel. Transverse waves vibrate right angles or perpendicular to the direction of travel. Total internal reflection occurs when the angle of incidence is greater than the critical angle. Critical angle you can calculate 1 over the refractive index, and the refractive index can be calculated. Oh, we did it up here. I don't know why I repeated it up there. Right, so these are the main things. How did I forget? How did I forget this? Right, you've got electromagnetic spectrum. It consists of radio waves all the way down to gamma rays. So radio waves, microwaves, infrared, visible light breaks down into Roig, BIV, ultraviolet, X-ray, gamma rays, long wavelength, short wavelength, radio waves, long wavelength, gamma rays, short wavelength. And finally, that is it. Right, hopefully it'll make some sense to you. If not, اقرأ واكتب. Right, Assalamu alaikum.